Hi, global warming is one of the biggest concerns for the modern world. And renewable energy, including solar energy, has become one of the solid solutions for that. Solar energy can be used to produce electricity and heat by using solar cells. A solar cell is a new technology relatively, and which means that there's plenty of room for development. That means that it gives good result and it's promising technology, but still there's many limitations that we need to overcome and investigate. And that's what we do. I'm Suheir Nofal. I'm a doctoral researcher at the Institute of Energy and Climate Research at IAK 5 at ULISH Research Center. And within the following minutes, I will give you a short introduction about my topic entitled by The Dynamics of Hotspot Formation in CIGS Thin Film Solar Modules. As you can see from this title, I'm working with one type of solar cells called CIGS. I'm not only working with simulation, but also the experiments related to that. And that's what I will present now. Starting from scratch, a solar cell is a device that converts light into electricity. And that's done by using semiconducting material. Each type of solar cell got its name from the material it's made from. And with the development stages, with time, it can be classified into generations. The first generation, it can also be called as traditional or conventional solar cells, including mono and polycrystalline silicon. It can be also called wafer-based solar cells, and that's because of its high thickness. It has high efficiency, but we can still improve that by reducing the manufacturing cost. We can reduce this manufacturing cost by reducing the thickness. And that's how the second generation started. The second generation can be also called as thin film-based solar cells because of its low thickness, which is only a few micrometers. And that includes amorphous silicon, cadmium telluride, and copper indium gallium selenide, or in short, CIGS. The third generation is still under development, but it's mainly made of organic materials. I'm dealing with copper indium gallium selenide, or CIGS. And the most common way to produce this type of solar cells is by using glass as a substrate, molybdenum as a back contact, which is a high conductive material, P-type CIGS as the absorber layer. CIGS has a direct band gap with an energy of 1.15 electron volt, which means that we can achieve a high efficiency by using this low thickness for the material, which also means that we can also replace the glass with a flexible substrate like polymers. After that, cadmium sulfide can be used as the buffer. Aluminium-doped zinc oxide can be used as the front contact, which is also a high conductive material. After that, laser scribing can be used to divide the large area into a series connected solar cells, and by that we can form a solar module. A CIGS solar module has a record efficiency of 16.7% for now. But despite all these advantages of low thickness and high efficiency and plenty of room for development, we still have some limitation to overcome, like the problem of shading. Under shading, one or more cells can be reverse biased, and by that, the solar module can be driven into a junction breakdown, and with time, this will degrade the performance of a solar module. As a result of this shading, a very small area will be more conductive, and all heat will, and all power will be dissipated locally in this small area. The generated heat from this power cannot flow away because of the low thickness of CIGS, and the hotspot is formed. The problem is not only the formation of a hotspot, but also the number of and the location of these hotspots cannot be really detected. And by that, the solar cell will be permanently damaged. So as we can see from that, both thermal and electrical aspects are strongly involved in this mechanism of formation for the hotspots. So when I say that I want to build a model, I need to build both a thermal model and an electrical model. I need to combine them together, and as any other type of simulation, I need to calibrate and verify this model by using experiments. For the electrical model, I'm using a term electrodes for describing the front and back contact, and in the electrical model, I'm presenting that as a network of resistors. At each segment, these electrodes will be combined together with CIGS layer which is presented as a one-diode model. The defected area will be presented as a shunt or a resistor in the electrical model, but it will be presented as a hotspot in the thermal model. Then, by using these thermal and electrical properties, I can combine the both models together. In the electrical model, I need to investigate the radius, the location, and the number of these hotspots, and all other temperature-dependent parameters. While in the thermal model, not only the temperature that should be investigated, but also the time to reach a certain temperature. Then, after combining these two models together as a thermoelectrical model, comes the calibration of this model by using experiments, and in my case, I'm using low-gain thermography or LIT experiments. And for these experiments, you can see the solar module, and it's connected to an excitation source. The excitation source is used to generate a heat distribution at the surface of the solar module, while a camera is used to detect the hotspots by generating thermal and low-gain images. After that, the data should be exported and analyzed and compared to the simulation. If that's done well, then I can start using the simulation to really investigate the different parameters. So, to summarize what I said till now, I'm working with one type of solar cells. It's CIGS. It has high results, but still we have some limitations, like the formation of hotspots. And for that, I need to investigate the mechanism of hotspot formation by building a thermoelectrical model and calibrate that with experiments. After that, this model will be used to investigate the parameters and extrapolate the formation of hotspot without really breaking the solar cells. If it works well with one type of solar cell, it should be valid for other types of solar cells, and that's the big goal. Thanks a lot for your attention.